let's get started. Good afternoon. Welcome to the session on Delta Lake migration at scale. Our presenters today will be Miao Wang and Dilip Biswal from Adobe. Miao is a senior engineering manager. Dilip is an architect, and they've both been contributors to Spark, and they'll be talking about the challenges they face migrating to Delta Lake and how they solve those problems.
Thank you. Hello, everyone. Thanks for joining us. It's my first on-stage presentation after the 3 years. Super excited. We will present a large-scale data migration. So I'm Miao Wang. I'm engineer manager at Adobe. Dilip is, I will co-president with my colleague Dilip, who is the senior engineer and architect at Adobe. So our talk will be divided in two parts. In the first part, I will try to answer a question why we need to move to Delta. It is divided into three subsections. One is the introduction to our Adobe Experience Platform, or AEP for short. The second one, I will cover the Adobe Experience Platform 2.0 architecture, then our journey to Delta. The second part, Dilip will present the technical part about the zero downtime data migration and share a scalable migration showcase. We hope to leave 5 or 6 minutes for Q&A. So let's start. This picture shows a high-level overview of Adobe Experience Platform and applications. On the left side, like many others, we enable our customers to ingest their data into our platform via different source connectors in stream or batch. In the meantime, our ingestion process will do validation, transformation, and store data in the data lake, which makes the data actionable for our downstream applications. So, I want to walk through a few of the examples of our applications built on top of the EEP. First, I will quote our products team's description of what our goal. Our goal is to provide the customer experience personalization at scale. So let's work through one example here. The customer journey analytics. It's our customer analytics solution that help you quickly understand your customer journeys online and offline, giving you the insights to meet your customers with incredible real-time experiences at scale. The second application on top of it is the real-time CDP. The CDP stands for Customer Data Platform. So it enables a customer to stitch data from different sources to create real-time profiles and activate the profiles into the pre-built segments that the user can select from the real-time CDP user interface. Most recently, the real-time CDP can leverage Adobe's new Sensei generative AI service in the Adobe Experience Cloud to automatically generate multiple variations of rich audience segments that can deliver to millions of users with incredible precision. The third application in this figure is journey orchestration. It allows you to tailor individual journeys to every customer based on their previous behavior and experiences. All these are made possible by our data lake, which will be the center of this talk. So before showing you the architecture of our data lake, let's take a glance of the data volume of our data lake. 220 billion real-time events per day, multiple regions in North America, Europe, and APAC. We have multiple petabytes monthly data ingestion. We receive millions of data deletion and update requests every couple of days. We have hundreds of thousands of tables per region. At this scale, it's very challenging to read, write, and manage the data. It's even more challenging now to moving this hundreds of thousands of tables from one format to Delta. This is our data lake architecture. We adopt the lake house architecture. In the center is the lake house. It mainly has 3 components. The storage providers, for example, the Adobe Data Lake service. The second layer is the the lake providers. Now we support both iceberg and delta. The third part is our experience platform access control. It's a homegrown access control. So all the producers and the consumers access and the data management access our lakehouse through a very thin API layer called the Platform SDK, or PSDK for short. The PSDK abstracts all the implementation details of a lakehouse. So therefore the lake provider and the storage providers are transparent to our users. So our platform evolves from AEP 1.0 to AEP 2.0. The AEP 1.0 infrastructure is based on a fork of Apache Iceberg 0.6. So in this figure, all the blue APIs are supported by AEP 1.0, which indicates that it's append-only data lake. When we say append-only, it means that if I want to update or delete one record of a file, I need to rewrite a new file to replace the existing file. So for AEP 2.0, we want to support the record-level operations. This it's only possible because of Delta. So let's see. In the next slides, I will cover the reason we need to support the record-level updates. But let's first go over the new APIs introduced in AEP 2.0 powered by Delta. On the producer side, we support updates, deletes, and merge. On the downstream consumer side, we support the read transaction and the read delta. So when the producer writing the changes to the lake, the change feeds will propagate to the downstream. In the data management layer, we add the create, optimize, delete, merge, expire, and update operations. So there are two reasons driving us to support the record level updates and deletes. The first part is our feature requests from customers. For example, change the data capture. It is a primary key-based operation for a single data set, and change propagation will be passed to downstream, and the downstream consumer can do read the data and do time travel. The second reason is to support the cost-effective updates and deletes in the system. For example, the GDPR in the AP 1.0, as I said, append-only lake, we have to rewrite the files multiple times to delete records in a file. The data hygiene is a new feature provided by our AEP 2.0 that allows users to do the record level fix of their data. There are another category of applications about the dataset TTL, data TTL that allow us to expire the records older than a certain amount of time. These are all the reasons we need to move to Delta. So moving to Delta is not, that happened one night. It's a long journey. It actually started in August 2020, the first time we received the record level updates requirement from our customers. So our architect group, led by Sean, sitting in front row, come up with the change data capture design in November 2020. Now, at that time, we face a question, how we implement this change data capture in our system. We are considering two options. One is iceberg, the other two is Delta, which represents build or buy solutions. To answer that question, in December 2020, we started a Garage Week project to integrate the data into our system, to run some queries. Then the whole Garage Week actually extended until February 2021. Let me show some highlights of these results. So we run the queries against some synthetic data of similar to our customers' workload, running against iceberg, which is the green bar, and on Delta is the blue bar, and the orange bar is the Delta with optimized. From this table, we see among these queries, some queries iceberg perform better, some queries Delta perform better. We conclude that at that time, Delta is comparable with iceberg. Later on, we do another level of evaluation. We enable Photon. Photon really blow away our minds. See, for example, for some first, Photon is the orange bar, always outperforms Delta optimized and iceberg. And for some queries, it even provides 7 or 8x improvements. It gives us a great potential that we can leverage Photon to improve our query experience. So by end of February 2021, we decided that we technically want to move to Delta to implement our change data capture features. So the next step, we are trying to convince our executives Delta is the direction to go. Therefore, from April 2021 to September 2021, we work closely with the Databricks team and the Delta team to evaluate whether Delta can support all our workloads instead only the one we evaluated in February. So we get a strong support from Databricks leadership and the Delta team. So we did 45 POCs covering from read, write, and the table maintenance. Then Databricks helped us finish the 21st feature request to fill in any gaps we identified in this process. So by end of September 2021, so we decided that we finally decided that Delta will be the center of our AP 2.0 implementation. In the meantime, we asked Databricks to open source a few features that we used in Delta. But Databricks always surprised us that open source all, that let us know in September, which was announced last year. So then from the beginning of October 2021, we started integrating Delta into our platform SDK, and then trying to asking people to upgrade to new PITK version and Spark 3 to use this feature. So by March 2022, we finished the Spark 3 upgrade, and what is more importantly, we engaged 21st our upstream and downstream dependency teams to validate the Delta on their workloads. So from June 22 from April 2022 until June 2022, we started the controllable deployment of Delta into our production system. I mean, the route is not always as smooth as we expected. There are many issues we are addressing with Databricks team. Let's show one example. So in one of our important customers, that show us a few queries, which let's see, they call it regression. See that the blue bar is the iceberg, the orange bar is Delta without any optimization. We see that iceberg constantly performs much better than Delta. So in that time, we work very closely with the Delta SQL team to analyze the issue, to compare the issue. The reason is that by default, the iceberg file data size is 1 GB. By contrast, the Delta is 256 megabytes. For this use case, it will generate more files on disk and slow down query. So since we can use the optimization function provided by Delta, we can rewrite the files with a similar size. In that sense, we can say after the optimization, we see Delta actually performed better than iceberg. So actually, we push the boundary. We are not stopping there to see. I see Delta beats with iceberg with minimal optimization. We tried other optimization options. So on my left, the one if we enable all the optimization, we can see the TCO of do the same query actually drops from $24 to $4. It's incredible results. So from July 2022, we started migrating our internal customers to further validate Delta. So and also sharpening our tool of do the massive migrations. So from March 2023, we started the massive migrations in production. We already achieved a lot. Now, I think next one I will give the presentation to Dilip. Let him walk through the technical details how we achieve the large-scale Delta migration.
All right. Thanks a lot, Miao. And thank you, everyone, for joining this talk today. So let me. All right. Before I start to discuss the current migration, I would like to share some of our experience with the prior migrations. So about 2.5 years ago, we actually were doing exactly the similar kind of exercise, migrating our platform's data from Parquet to Iceberg. At that time, though, we did not have a concept of zero downtime migration. What that means is that we had to take the dataset completely offline before we actually migrated them. That also means that we had to work on a schedule with each of our customers because we are taking their datasets offline. So furthermore, we kind of, when I look back, we designed that infrastructure in a bit of a hurry without thinking about the monitoring and auditable aspects, and we often found ourselves, live debugging the datasets while it is in offline mode. Now, if we could fix the problems in time, well and good. But if not, then we had to renegotiate a new downtime from our customers, which was quite painful, frankly. So the challenges that we face today, though, are far greater than the challenges we faced a couple of years back. And there are two reasons for it. First thing is the number of customers that we have today are far greater than the number of customers we had 2 years back. And the second thing is that the size of the datasets have grown in the order of magnitude. So taking the learnings from our past experience and looking at the current challenges that we have, we kind of set ourselves these goals when we design the migration. The first thing is the zero downtime. Basically, it allows the migration, the source to mutate while we are actually migrating them, except when we enter the critical section. Second, resiliency. We wanted the migration to be tolerant of failures, and we wanted the ability to restart the migration from the last failure point, as opposed to starting from start. Third, monitoring. We wanted to be able to monitor all the ongoing migrations and send out alerts if there are any problems. Fourth, rollback. So we wanted to be able to, we wanted to have the ability to revert a previously successful migration by going back to the previous table format. And fifth, auditability. So here, as part of migration, we wanted to keep all kinds of migration metrics so that we can report on them, or we can also do analysis on them. And finally, because the scale of the data that we are dealing with, we wanted to have the entire, all the components fully automated end to end. And that brings us to discussing automation. So in AEP today, we have hundreds of thousands of data sets. And obviously, also we wanted to migrate them on a schedule. What that meant is that we could not afford to have a single manual component in the entire workflow. And to automate, we made use of Databricks workflow to help orchestrate and schedule the jobs for us. So migration can be, for a customer, can be initiated by using a simple migration CLI, which then schedules a job called migration supervisor job. What this job does, it actually scans a lookup table and finds out all the necessary sandboxes that it needs to migrate. And for each of these sandboxes, it schedules another supervisor job. And this sandbox supervisor job actually does the similar lookup on a lookup table and then finds out all the data sets that we need to migrate, and then it schedules a task for each data set. On the right-hand side, we see the migration task. Actually, conceptually, it's pretty straightforward. We are basically reading from the source, and we are applying on the target. And after post-migration, we collect all the migration output and store them in our system table so that we can report on them or do some analysis. So here we see a simple Databricks UI where we show a migration, active migration for a customer. All the rectangles represents a migration task for a data set. And here in the screen, we can see all the rectangles are in green status, meaning we seem to be doing pretty well for this customer. But if there are problems, then the migration supervisor job is responsible for sending out the alerts for us to be able to react to them in timely manner. So this brings us to the zero downtime migration. Now, in our platform today, we have quite a few data sets that are very large in size. Some of them are bigger than like 500 terabytes. So to obviously copy that large amount of data will take time, and we did not want to take our datasets offline for the entire duration while we're copying the data. That's why this feature was very critical for us. And the way the steps are like, first we go through a process of initialization where we provision the target table. In this case, it is in format delta. And then we make sure we create the table with right set of partitioning columns and right set of system columns. And once the table is initialized, we enter what we call a data copy loop, where we actually read all the incremental chunk of data from the source, and then we apply it on the target. While applying this data, we make sure we checkpoint the last process or last seen snapshot from the source into the target. And actually here, Databricks has an option called user metadata that we can pass it as a user-supplied option to the data frame write operation. And we make use of this to supply the source snapshot ID that we store in the Delta's transaction log. Now, in every iteration of this data copy loop, we also try to find out whether we can enter a critical section. Now, how do we know when to enter a critical section? Well, we can apply a couple of different heuristics, but what we have implemented in the platform is a very simple heuristic that says that the time it takes to apply the last incremental chunk of data is less than a particular threshold, then it is okay for us to enter the critical section. Currently, that threshold is defined to be 3 minutes, which means if it took less than 3 minutes to copy the last incremental chunk of data, then we enter the critical section. And the very first thing we do after entering the critical section is basically we log the table. At this point, we do not allow any mutation of the source. And we are in a steady state, so at this point, we are ready to copy the last incremental chunk of data and apply it in the target. And at this point, the source and target should be in agreement. We make sure of that by comparing the row counts and also partition counts. Once the data integrity check is complete, we enter a finalization phase where we record the new table format in our catalog. Here, one small point I would like to mention about the locking the source table behavior. So this functionality is not available in the Iceberg open source. We at Adobe maintain a fork of Iceberg, and we have a lot of features that we have added that to support Adobe's use cases. And this is one such feature that we had to add specifically for migration. So let us see this by a simple animation. So we start with the iceberg table, which has 4 rows represented by 2 snapshots, S1 and S2. At this point, we are ready to migrate. And like we said, first we enter initialization phase where we provision the delta table. And after that, we copy the first incremental chunk of data to the target. Here we can see we applied these changes in one transaction with a version 1. And we also see that we checkpointed snapshot S2, which is the last seen source snapshot that we processed. At this point, let's assume that at the source, 2 more transactions are added, S3 and S4. So in the copy loop sees that and copies them over. This time checkpointing S4. Now let's say there is 1 more transaction, S5. And at this point, let's assume that it is okay for us to enter the critical section. If it is, then we actually log the table and we copy the last chunk of data to the target. This time we checkpoint S5. So at this point, the source and target should be same, and we make sure of that by comparing row counts, like we said, and then we record our new table format in the catalog. And the migration is complete at this point. Now, let's discuss offline migration a little bit, but I would not like to spend a lot of time discussing this because it is obviously a much simpler flow. In this flow, just like we did in Parquet to Iceberg migration, we basically block the source for the entire duration of migration. It blocks the source and then it copies all the data at once. But then the question is, why do we have this option? Well, I could see 2 use cases for this. let's imagine we have a data set that is fairly small in size and is actually not changing that frequently. In that case, we can actually use a much simpler workflow to copy the data over, as opposed to the other workflow we discussed, which is slightly complex in nature. The second case where I can see it being useful is, if let's imagine a data set that is medium-sized, but is very fast changing. There's a lot of transactions in quick interval. So in that case, it is very much possible that we do not get a chance to enter the critical section. If that happens, then we can use this flavor of migration. However, we have done close to what I would say 30 to 40% of the migration, and we did not have to use this option so far. That brings us to resiliency. So like we said, we do have very, very large tables that we need to migrate. And some of them are more than 500 terabytes in size and takes, so the jobs to copy them sometimes takes days. So when a job takes that long to complete, so obviously it is more prone to transient errors. What I mean by transient errors are like, for example, temporary glitch in ADLS or temporary glitch in any of our dependent services. So obviously a job that runs for that long is more prone to seeing these errors, and we wanted to make sure in that case we want to sort of every time we run the migration we want to make progress. That's why we use this checkpoint way where we resume the migration from where we left off. So as far as errors are concerned, there are two kinds of errors that we can see. One is failure that we can see before we enter the critical section. The second kind of error can happen, the errors that happens after we enter the critical section. For the first kind of error, we can simply, like we said, we can simply retry the migration and it starts from where it left off. For the second kind of the error though, we do have to manually inspect the error, and if it is a transient error, we can very much retry the migration, but if it is not, we may have to manually look at the root cause, find the root cause, why this is the failure is occurring. And if we cannot fix it in time, we can consider a rollback. Here when I use rollback, it's actually different than the rollback I'm going to be discussing in the next slide. Here I'm talking about rolling back a active migration or the current migration which is not complete yet. So in this case, the way to recover would be to simply unlock the table. Like we mentioned, when we enter the critical section, we lock the table. In order to recover for error from critical sections, we just have to unlock the table, and then that allows the transactions to happen on the source. And at this point, the data that we have copied so far, we can discard it or we can keep it if we have to do some debugging. Now, this brings us to rollback. So like I said, this is a feature that allows us to roll back a successful migration. The question is, why do we have to ever need this feature? Why do we have to roll back a migration that has been already successful? So like Miao mentioned, before we entered this migration phase, we had this phase where we ran about 45 use cases, Adobe's use cases against Delta to make sure, basically that exercise was to identify if there are any gaps in Delta in terms of addressing Adobe's use cases. And we did find quite a few gaps, and we worked with Databricks to make sure all those gaps were addressed. The point is, at the point we are doing migration, we were quite sure that we are not going to hit much of functional issues, but we could not say the same about performance issues. As you guys know, Iceberg and Delta are two different data sources as far as Spark is concerned. And we also know every data source has got its own push-down predicate semantics and also can have different data skipping techniques. The reason being they organize the metadata completely in a different way. So it is very much possible that post-migration, a query that ran quite fast on Iceberg suddenly is running slower in Delta. And we wanted to have an option to recover from this. And that's when we will use this rollback option. And the way we do is, the implementation is quite straightforward actually. We log the delta table. Currently, we do that by installing a check constraint that refers to one of the system columns. We do recognize that this is probably not the right way to implement a log table. That's why we have a pending request against Databricks. Hopefully, they will help us implement this. After we log the source table, we basically read all the changes that has happened on the delta table post-migration and apply them, convert them to equivalent iceberg operation and then apply them on iceberg. Once the data is copied, we basically make sure we validate the integrity of the data, and finally we record the new table format. In this case, we switch the table format from delta to iceberg. On monitoring, we do two kinds of monitoring actually. One is monitoring the active migration, basically monitoring the critical section. Like we said, we make every effort to make sure we do not take the dataset offline. We want to keep the dataset offline for as little time as possible. So this was very important for us to monitor to make sure no datasets is actually staying in the critical section for a longer duration of time. The second kind of monitoring that we do is basically monitoring a dataset post-migration. So there are basically two things that we are verifying. One is the dataset post-migration is actually writable, meaning there are actually snapshots that are being produced. And the second thing we verify is that datasets post-migration is actually readable. We do that by incrementally reading the data for a period of time. So here is a screenshot that shows the critical section monitoring. It's a simple scheduled job on Databricks that runs every hour, and its purpose is to basically look for datasets that are in critical sections and make sure to send the alerts if any of the datasets violates the SLA. And if a dataset violates the SLA, then an alert is sent out which looks something like this. Here, the alert actually has details about the customer, the sandbox, and the job also, job ID. All right. So we did say that for auditing purposes that we actually collect a lot of migration metrics and store them in our internal system table. We can obviously do different kinds of queries. And here is a simple query that I've done to just know the state of migration for a given customer. As we can see, we have migrated a large amount of data sets to Delta already, but there are some that are in iceberg or Parquet format, which we have to act upon. And this one, all right, so I think I'm at the end. I would like to pass it over to Miao for key takeaways. Thank you.
Yes, thanks everyone for attending the session. I just want to say, share some key takeaways from this migration process. First one I want to share is that no technology fits for all solutions. That leads to a second takeaway is that don't only trust your public benchmarks or any published benchmarks. Trust your own benchmark, build your own benchmark. The third one, in my career at Adobe, I go through different migrations, storage layer migrations, Parquet to iceberg migration, iceberg to Delta migration. All the thing I learned is that, number one lesson I learned is that if have a zero downtime solution will greatly reduce the frictions and also reduce the community cost with the customer and make the migration successful. The last one is that I think when we make a technical decision, the strong partnership and strong support team are very important. Is a very important factor. I want to give kudos to our US team, Bucharest team, and to Databricks team because it's very geographically distributed teams, but we work as a same team to make the thing happen. We are relatively small, but we make big achievements. So here's our contacts. If you are interested, you can shoot us messages via LinkedIn or we are over open to make connection and share ideas. I do have one backup slides. I mean, this is kind of issues. Top 10 issues in my mind that is critical for the success of data migration. I want to read through all of it, but the major thing is that the behavior between iceberg data is different, and then we need to fill the gaps. It only possible because we have strong support and partnership with Databricks. Yeah. Thanks, everybody.